Let's see. Good morning, everybody. Step on in for those that are outside the door. Yeah. All right. Yeah. So I definitely have the pleasure, and sorry, I'm going to have to slip on my glasses. These days I can't speak without them or read without them. So I have the pleasure of introducing Dr. Richard Bishop today, who will be giving our seminar lecture. Richard Bishop is a geologist who has worked the spectrum of research, exploration, and production for Unocal for 2 years, ExxonMobil for 29 years, and as a consultant independent for 15 years and is now retired. Although we were just talking, you never really retire, do you? During this time, he has seen the world both as an explorationist and as a synthesizer of global exploration opportunities. Dick has published on mechanics of piercement diapierism, origin of abnormal pressures, assessment yardsticks, material balance of trap assessment, source overcharge, world oil supply, and the origin of supergiant fields. Dick is past president of the American Association of Petroleum Geologists and the Houston Geological Society. He has been recognized with the AAPG Sproul Award, is a distinguished alumnus of the University of Missouri, an honorary member of both the AAPG and HGS, and was named a Legend of the HGS. He is a recipient of the Cooley Award from HGS and is a recipient of the SBE Legion of Honor Award. Dick earned his PhD from Stanford, his MA from the University of Missouri, and BS from Texas Christian University. With that, I welcome you, Richard.
Thank you very much, and thank you for the invitation to be here. I must define what the title is up here. The supergiants are fields that are greater than about 2 billion barrels. Can you hear me with this mic? Okay. So how did that happen? You've seen probably 5 billion barrels as a supergiant cutoff, but the 2 billion barrels has a history. Geological history. And years ago, when I was doing some assessments on some detached fold belts and things like that, I noticed that none of those fields were bigger than 2 billion barrels. And so I also looked at the extensional, and they didn't have much in the way of 2 billion barrels. And so my conclusion was that if you're going to get bigger than 2 billion barrels, you're going to have basement involvement. So that was a little factoid I carried around. And one day I was at a very hoity-toity AAPG meeting. Hoity-toity means that there was an open bar. And I was talking to the head of intergalactic exploration for an intergalactic company. And I told him this little factoid. And his response in 2 syllables was baloney. And so then I knew he was a smart guy. I'd known him a long time. So I figured he's been in management too long. So I went to one of my intergalactic consulting friends, told him the same thing, and he quoted the first guy. So along came the pandemic. I thought, gee whiz, this is a good opportunity. I'll show those guys. It'll take me a month. Well, I was right about the month, but wrong about the other couple of years. This is some data. I know that the graphs are small, but they're all the same size on here, probabilities and volumes over here. But basically, these are all detached extensional field sizes. In the Niger and in the Gulf of Mexico, we don't see any fields that are greater than 2 billion barrels. Now, there are some over in Angola, 2 or 3 over there, and in Campos over there, but those tend to be field complexes. You know, it's a whole block kind of a thing. So they're not really a discrete field. So that's the kind of data that I had looked at. And I'll show you some more data on the fold belts in a little bit. So what are the conclusions after looking at these things? The first is that the SAG event, and there are lots of different types of SAG, and I'll show them to you, are very significant, associated with the transgressions, but in terms of creating reducing risk and actually creating hydrocarbon systems. Mesozoic sag and sea level rise of the post-breakup of Pangea created about 2/3 of the supergiant fields of the world. And the basement involved features dominate both the number and the maximum sizes of those fields. Now, trap size and seal area, not the source rock, determine field size. So what are the applications in here? Well, these apply, what I'm going to show you, I think applies to prospects and plays at literally all scales in terms of just improving exploration and development efficiency and improving the way that we do our risk evaluations. And secondly, all these things apply to, I think, probably to CO2 storage as well. So acknowledgement in here, Mike Horn built the first giant fields database, and that was back in 2003. But John Dolson revised it. I was talking to Charles Sternbach, and I was telling him what he was doing, and I was using Mike Horn's database, and Charles told me that John Dolson was revising that database, and I didn't know John. And Charles contacted John, and the result was that John let me use his database before it was published. So I'm deeply indebted to John Dolson. Very generous of him to do that. So all the data that you see in terms of field sizes, field ages, and field locations up here all come from that giant fields database of John's. And I also had two silent co-authors on here. I'd written the manuscript, and I was struggling with how to put all this stuff together because it was large and awkward. And I didn't know Jim Lowell very well. I met him once on a street corner in Calgary at a convention. But anyway, I called him up and asked him if he'd look at the manuscript. And he's the co-author, along with Todd Harding, on the structural styles. And he did. And then he said, but I want someone else to share the blame on this. And so he roped Richard Groshong into doing it as well. So I'm deeply indebted. But most of all, Edie is my bride. We've had more than half a century together now, and she put up with a couple of years of me doing all this kind of stuff. So that was very patient of her. So these are the 255 of the roughly 1,200 all giants. Now, when I talk about giants, the giants are basically 500 million barrels and higher. The supergiants are greater than 2 billion, and this is a map of just the supergiants in here. And you can see on here that they take about 22% of all the giants. They are in about 1/3 of all of the basins with giants, but they contain about 73% of the reserves in all the giants. This is a significant volume in here. Now, the other thing, in terms of just an aside, as you look at the map on here, you can see there's a high concentration of supergiants in this area. You'll also recall that those areas are have very low populations. You can measure the populations in several hundred millions of people. Off to the east is the half of the world's population, over 4 billion people, India, China, Indonesia. Now, these folks are not doing anything to reduce their carbon footprint. These volumes over here are going to go over there someday. Now, how that's going to happen, I have no idea. But in terms of just geopolitics and geoeconomics and geology and hydrocarbon fossil fuel geology, this is, I think, an important thing to consider in the future of the world the next time you're writing that out. Okay, part one, what makes supergiants? Okay, it's very, very simple. And it's the smaller of the trap size or the charge. And that's all there is to it. And this is true if you're dealing with oil and gas, if you're dealing with uranium, or if you're dealing with soda pop. It's always the same. It's just as simple as that. We published this about 40 years ago, and it's been completely ignored by industry ever since. So we're going to focus on trap size. Now, sometimes when I say that, people get a little concerned, but what's the evidence? And there's a lot of evidence of overly filled traps. And it's been around since the beginning of the oil patch. The first one, the trap's filled to the syncline of spill point. If you have a trap that's full to spill, it has overcharge. Secondly, are fault leaks. Remember the Allen diagrams, cross faults and up to fault? All those leaks, all those traps that leak are full. And the implication is overcharge. Seismic chimneys. I've had some people tell me they've never seen a full trap in my life. And I ask them if they've ever seen a seismic chimney. Nobody will admit to never having seen a chimney. But seismic chimneys indicate full traps. One that's really kind of subtle on there are non-associated saturated oils. Now, how does that, you've got a fully saturated oil on here. Anytime more gas goes in there, what happens? It leaks out. So that trap is also full. Our source yield calculations, they also show overcharge. There are several of them in the literature, and they will see anywhere from 5 to 20 times as much hydrocarbon generated as is captured. Gas can displace oil is another indicator, but one down here is that the contacts show where the trap limits are. People don't always recognize this, but the contacts tell you where the leaks are. So if you're going after attic oil and you push that oil below the original gas oil contact, you might not get all your gas back. So the contacts are telling you where the leaks are. Now, what about the alternative on here? The traps are not filled to this, not fully charged. That has to happen, but it's kind of rare. It has to, the first molecule that goes into the trap, that trap is truly underfilled. But it's very, very difficult to identify. This word underfilled is imprecisely used. And historically, it means it's not filled to a spill point. But is it not filled down to a leak point? And we can't find that spot very easily. That's a very, very difficult thing to do, if not impossible to find. So is this kind of data on here is very hard to locate. So it probably exists out there, but it's probably not a real common occurrence. Now, there are traps that are just indeterminate. You can't tell. They're so complicated, particularly stratigraphic traps or a one well field. You just don't know. So there's a lot of traps that you cannot know the answer to. But one of the reasons for looking at the supergiants on here is that they're big enough that you can actually tell what they look like. You have enough data on a lot of these. Now, this is an example in here of leakage and spillage. This is from Borneo, and this is a plot on here of depth. And this is oil fields here in green, and they're the ones that have the chimneys. And the gas is basically leaking from the fields and leaving behind saturated oils. As we go deeper, the seals become better, and they're sealed with gas. And so down deeper in here, we find the gas fields. So what is happening here is that the trap, not the source rock, is determining oil versus gas in the container. Now, when we look at traps, this is typically a prospect, but actually it's two prospects. The top one up here has four-way closure. It has to have top seal. The three-way closure down here has to have top seal, but it also has to have fault seal. Now, the fault seal is a binary. It's either there or it ain't there, one or the other. Now, typically, the way we do our prospecting is make it a continuum like this, or like the sea. But what we're showing here is that you break it into two, and you specifically say, well, what's the chance of the fault sealing? And in this case, it's about 20%. Now, you notice the volumes are the same, but the probabilities are different. So when you treat these leaks on there as binary, you can actually get a better handle on the interpretation for the fault leakage. And when we have oil and gas available, all these things are possible results in a single trap. And you end up going through a decision tree, something like this. And if you're into AI kind of work, you're going to be building things that look like that. So if the trap is our problem on there, and we got what makes supergiant traps is the next one. So we need a tank, and we also need a seal, and that's caused by sag. Now, what is sag? There are lots of types of sag. Normally, when we say sag, we're talking about post-rift thermal sag. And in this case, what if we have syn rift sediments over here, the timing along this above the syn rift and the sag is really very, very close in time. There's not much, a few million years, whatever on there. In the EPEIROGENIC sag over here, this unconformity in here can be a few million years, or it can be hundreds of millions of years different. So there are different processes. This sag on here will last and usually remain in the realm of tens of millions of years, 30, 40 million, 50. This stuff over here sometimes will go well over 100 or 150 million years. It can last a very, very long time. And this is one which is new to me because I didn't see it before I started doing this stuff. But this is tectonic sag. I call it tectonic sag. I'm not sure what the right word is. Some structural geologist is going to come in there, tectonic sag, and figure it all out. Well, what happens is we have this compression over here, and immediately following that compression, this stuff gets filled in. And what the implication here is, we have all this compression, and then it's followed by relaxation. And I'll show you several examples of this. Oops, that one was just extra. What created the many supergiants? The sag. This was subsidence without significant faulting, and this global rise of sea level and the transgressions through much of the Mesozoic. Now, this is a map of all of the giants, and one third of the 1,100 plus giants are Cretaceous age, have Cretaceous age reservoirs. This is just looking at the supergiants, and if we look at just the Jurassic and Cretaceous, over 57% of them are Jurassic and Cretaceous. High concentration. The Cenozoics over here, these are basically that tectonic sag I was talking about. These guys are a separate cat. These guys are basically, most of these are in the extensional environments, and these young ones over here are in the compressional, formerly compressional. And this, of course, is sea level curve of Vale and Mitcham. You can see this huge rise. The highest sea level throughout the Phanerozoic was here in the Cretaceous. But stop and pause and look at the coverage on here. And this is middle Cretaceous, the Turonian from Scotief's work. And everybody knows about the North American sea level or Cretaceous seaways. But man, look at this. Look at these, West Siberia over here. Asia's cut in half. Europe is completely flooded. Africa's cut in quarters. Latin or South America is almost split east-west and almost split north-south, along Patagonia as well. Arabia is completely flooded. So this covers a lot of territory. And what's going on at this time is both post-rifting thermal sag is continuing various places. You also have this rise, and EPEIROGENIC sag is also occurring in a lot of these places. If 85% of all the supergiants have some sort of sag associated with them. Now, this is the age at the base of the sag, at the end of the faulting or the transgressions in here. And 66% of these are Mesozoic in age. And this is the concentration in here. These are a number of fields on here, but you can see this high concentration from the Triassic through the Cretaceous in here. And again, the Cenozoic stuff, this turns out to be mostly tectonic sag. And this is fields by their structural styles. These are completed rifts concentrated in the Jurassic, failed rifts concentrated in the Cretaceous, arches and domes, EPEIROGENIC basically, and it's concentrated in the Cretaceous. And then just the simple clastic stratigraphic traps are also Cretaceous in age and concentration. So what's the big deal about the sag combined with the rising sea level? look what goes on here. You know, I like to think of SAG as a Rodney Dangerfield of play processes making hydrocarbons. During SAG, the play elements, you increase the bed seal over the structures and over unconformities, particularly years and years ago. Actually, it was after I was born. Louis Weeks, 1948, talked about, he discussed the role of unconformities associated with very large hydrocarbon accumulations, and he couldn't figure it out. And he wrote about it again in 1952, and then he wrote about it again in 1958 with the habitat of oil. So the role of unconformities was a real mystery, but he didn't have plate tectonics, they didn't have sea level rise. And now we can see that's really the association of unconformities with these very large accumulations. Fault seal gets increased because, well, if you're going to stop the faulting, what happens? Well, the fault gets buried and the fault is no longer, it has bed seal on top of it. And the cross fault, they stop moving. You're not moving reservoir to reservoir to reservoir anymore. You're just, whatever's there, either seals or leaks. So all those things increase the trap volume. And at the same time, you're increasing maturation, and that increases the juice volume. So you're increasing the charge and you're increasing the trap volume all during SAG. And that means, it implies that you're going to have lateral migration and spillage. But during SAG deposition, we can also have deposition of other play elements in there, and also well as top tier source rocks. We all know about Jurassic and Cretaceous source rocks. And this is like coals to Newcastle. I thought it was pretty cheeky to put it in here to this group, but this is a cross section from West Texas. But it's such a nice example for what all the things go on with SAG. I just couldn't resist. Okay, this is the earlier the pre-Permian section is down in here. And with the Permian SAG on this stuff, that basically sealed the Ellenberger. The Gomez's, the Puckett's, those kind of fields over there basically get sealed with this evolution of the Wolfcamp. And within the Permian, well, you guys all know all about that. Multiple hydrocarbon systems are deposited within there. So here you have one SAG event, but there's the Silurian, the Devonian hydrocarbon systems down here, and then you have all the Permian hydrocarbon systems up there. A lot of stuff goes on just due to that SAG event. Where are in the rest of the world? Where's the pay zone? It's kind of equally split between being below and above. Now, that's how I view the origin of supergiant fields. That's what I think happened. Now I'll show you the evidence. And in general, this is what the data we have with structural stratigraphic combination. This level of description commonly is all we have, but it doesn't really tell us very much. So I merged on here structural styles with some standard stratigraphic nomenclature and try to describe the traps with a little bit more detail in terms of their structural history as well as their stratigraphy. And this is not a classification. This is just a way to describe these traps, and it's how I've done it. And most of these are pretty straightforward in here, but when you get to the combinations, I'm not sure that there are always unique answers to what these fields, how to describe these fields. But anyway, I have made a shot at it, and I'll show you some of the results. This is just looking at their stress environment. This is extensional to neutral, which is the EPEIROGENIC kind of a SAG. And you can 84% of these traps are in an extensional environment, with the other 16% over here in compressional. Field sizes. Arches and Domes has the world's largest field at 176 billion OEB. This is North Dome and Gutter. And I don't know how PARS is so close to North Dome, you might call those two one field. I wrote a paper on North Dome years ago, but we didn't have any data on the Iranian side. But that thing could even be up into the order 250 billion oil equivalent if those two merge. It's just absolutely huge. And failed rift, that's in West Siberia at Urengoy. And over here, the full belt. This is Zagros. And that's a very impressive kind of a size. So let's look at the arches and domes. And this is where most of the arches and domes are. Average field size of 14 billion. And there's the maximum from 176 at North Dome. And this is what a lot of these look like on here. And this is the Hercynian unconformity in here. And the range on here, look how long this subsidence occurs and takes on in here. Because it goes from the Triassic up into the upper Cretaceous. So you're dealing with 150 million years on here, really long-term subsidence. And this is to show you how much you can get between the time lost. This is a Cambrian reservoir at the Hassayar Mel with a Triassic seal. So you're dealing with 250 million years of lost time in there. So these arches and domes are different from typical rifts. This is just the opposite. You guys know this one, East Texas. All this happened in just a few million years between the sag and the uplift and erosion and sag and uplift again. But that's basically the basement moving on there in a very, very short period of time. And with, of course, sea level contributing to this thing. So there's no rule about these unconformities on there. They cover a wide range of time. Arabian platform. Now, the Arabian platform has been called a rift sometimes, and it has been. Some of these things have happened. It's also been called a foreland. A lot of these tectonic terms refer to something that happened and the way it is today, but it doesn't necessarily tell you what controlled the accumulation of hydrocarbons. This extension in here dies basically in Carboniferous Pennsylvania time. This is Northfield, the world's largest, and it's reservoired in the Permian, which is the cuff right in here. And right next door to it is the world's largest oil field at Gawar, and it's reservoired in the Jurassic. Now, when we look at the subsidence history of this thing, this is just really astounding. It starts back here, actually it even goes back to the Cambrian times, but here it starts around 450 million years ago. And this is only a couple thousand feet that it's dropping, but it just subsides all the way down to basically present day. The only thing that interrupts it at all is when it finally collided with Asia. So this is a very unusual subsidence history in here. Now, when we look at these arches and domes, the field size distribution here, this is the calculated, and it couldn't get close to matching it. So you say, gee whiz, what has happened in here? There's a gap in here between about 35 billion and 55 billion. And there are no fields in the world between 35 billion and 55 billion. There are 7 fields bigger than 55 billion. And 5 of those fields are on the Arabian platform. And these are arches and domes. Now, arches and domes describes the geometry, but arches and domes doesn't tell you how big these things are. We don't have words to say humongous. You just don't see that in the geologic literature, and it's not in the AGI dictionary. But what happens on here, these arches, this is the gutter arch, that's the Gawar arch, and these are various parts and platforms and arches within up near Kuwait. This is a Silurian hydrocarbon system. This one is a Jurassic hydrocarbon system, and that is a Cretaceous hydrocarbon system. But these things are on these swells and platforms. They're on very, very large structural entities. And when we go to the other two, Urengoy and West Siberia, that's a failed rift. But what happened was the rift basically lifted up a large platform. And so it sits on a platform within that rift on there. It's not a typical fault type of play. And the other one, I can't pronounce it. Osman is as close as I can get to it, but it's over in Amudarya over here. And it is a basement involved reef. So the reef is the reservoir. but it's supported by a very, very large platform underneath it. So it's these very large entities in the basement that create the opportunity for these very huge, huge fields. And this is their basement involved in carbonate buildups, and this is their distribution, and they occur pretty much in lots of places around the world. And this is an example from Sumatra, and you can see the basement involvement over here. And this basement, see, all these reefs are sitting on top of all these basement highs, and it's the basement highs on there that basically influence the size and the duration and location of these reefs on here. So that's why that's the role of basement on here, is in terms of influencing the dimensions of these things. This is another example from the North Caspian in here. This is TENGIZ and Kashagan over here. TENGIZ is about 8 billion and Kashagan is 19 or 20 billion, something like that. But again, this dark line over here is from Chevron, and they are outlining the basement highs that they're all sitting on. Purely stratigraphic habitats, basements not involved. These are clastics, and these are all pretty much Cretaceous in age, and you see several of them over here in West Siberia, and you see several of them over here in on the North Slope. And this is PRIOBSKOYE field in West Siberia, and this thing just sits on top of the Bazhanov source rock. But the top sets and the foresets and the bottom sets, everything on these clinoforms is charged. And one of the lessons from something like this is that we have to explore the whole clinoform. You can't just look at part of the clinoform, you got to look at the whole thing. And it also reminds us that we really don't know a lot about secondary migration. How does the oil get in there? And it's very, very difficult to figure out a way. And lots of times we have to say, well, we don't know, but we know it does. And this is kind of the thing that you have to believe in, because you know it can happen. Carbonate buildups are the same way. How does it get in there? I don't know. And these are more Cretaceous clinoforms. This is along the Barrow Arch, and this is where the PIKKA field has been discovered, and Willow and Smithfield. These are all multi-billion barrel fields. They're running in sizes anywhere between 3 and 6 billion barrels, but this thing is just loaded up with amplitudes all along here. So this is another opportunity on there to develop, see stratigraphic traps up there on the North Slope of significant size. Carbonate buildups, I could find only one, and that was in West Texas, and that was Wasson Field. Level and Slaughter might be in there too, but it's kind of close. But basically, it's very, very similar. You guys have worked this area. I don't need to tell you about it, but basically, it's the same sort of deal. The top sets, foresets, the bottom sets, they're all productive, can be productive, and it's just an example of the carbonate, pure stratigraphic. Unless you guys have some information on the basement, I asked Tom Ewing about it. He didn't say it was involved, so that's what I'm quoting by. Skip that. The detached habitats. Okay, detached compression and extension. Now, fold belts I told you about earlier. With newer data, Zagros was the big exception. Zagros fields are extraordinary. The only other fold belt that has a supergiant field in it is Margarita Field down here, and it's back near the hinterland, so it may have some basement involvement with it anyway. But let's look at just Zagros. Zagros is different, and this is looking at Santa Cruz and the Llanos basins in terms of number of giants versus their maximum field size. And the maximum field size for these two basins is 2 and 3 billion barrels. And they have about 5 or 6 smaller giants in them as well. But look at Zagros. It has 60 giants, and the largest of which is 34.5 billion barrels. This thing is unique in the world. I mean, it's a big dude. Field size distribution. Let's take a look at that. Why is this jumping in here? It goes from about 8 billion to about 15 billion. So you got all this group of fields over here that really don't quite fit the pattern. We look at typical fold belt. This is a typical fold belt, which is based on the Canadian Rockies. And you see these sled runner thrusts running up to the surface out here. Now this is a balanced cross section from northern Zagros, and you see these same sled runner faults coming up to the surface. But when you get to the leading edge, these faults are dying down here. And when we look at the largest fields within Zagros, these are 13 supergiants. They're greater than 5 billion. You can see a high concentration right near the leading edge of Zagros. And you compare that, don't blink, with the rest of the basin in there, and you see giant fields scattered throughout the whole basin. So my interpretation of that is that basically the Zagros is so young on there that these thrusts have not grown enough to cause those fields to leak and destroy themselves. We have a similar story with the wrenches and the upthrusts. They're scattered all around the world. You're familiar with a lot of these, I'm sure. This is from eastern Venezuela, and the one I showed you earlier. These are Mesozoic, Miocene reservoirs on these giant fields over here, and this is a Miocene tectonic sag. This is a surprise to me, but this is Wilmington Field in the Los Angeles basin. Same sort of deal. This is the pay zone down here. There's a small unconformity, brief, I should say, and this is the Pliocene sag on top of it, which is, here you are in the middle of an extremely active tectonic zone, and you've got a little quiet space. It's a safe zone. So it lets you know that it can happen. It doesn't have to be very big, but it can happen. I didn't have it up here, but the same is true in the San Joaquin Valley. You see exactly the same sort of very late sag on here, this tectonic sag. Now, this one is the Anadarko Basin and the Panhandle Field, or Hugoton Field. And this upthrusting in here was basically done at the end of the Pennsylvanian. And the same Permian sag that we saw in West Texas occurs here in Oklahoma. And this is the deposition of the Permian Reservoir. And this section over here was the Permian Seal, and then some Mesozoics on here. But this faulting in here basically stopped at the end of the Pennsylvanian. Now, there's lots of faulting, earthquakes going on up there, but they're not getting through and breaking the seal. So these kind of pauses and relaxations on there are, they can, once they start, they can last for millions of years. And there's always the exception. And this is along the South Caspian. And this is a very dynamic area along the Absheron Arch in here. And this, I think there are 3 supergiants. And these guys don't have any sag. They're being torn apart today, but they're still being charged at such a high rate that there's still supergiant fields over there. A very dynamic kind of a situation. So when we look at the wrench basins with sag and the location, these wrench related at the base of the sag, about most dominated in the Cenozoic. And location of pay is typically below the sag on here. But the reasons that these things are concentrated in the Cenozoic, I think, is because they're still active and they're in the process of self-destruction. It's a combination. This one is a mess. Here it's a thrust fault, and there it's a transpressional event after the sag. This thing has characteristics of both detached compression and basement involvement. There are strike slip faults associated with it. The shortest block is moving off to the northwest on this thing, or northeast on this thing. And the sheer dimensions of this thing are so much bigger that all other fold belts save Zagros in the world. So I think that this one is a combination in here, but we don't really know what basement looks like. We just don't know. But the implications are that it is involved, at least to me. And this is, we're going to show this on Monday, but basically we're looking around the Gulf of Mexico, Gulf of Mexico basin. This is the Florida Arch, and these are the Wiggins arches and various kinds of domes, Jackson and Sabine and Llano Uplift. Here's a combination. We have there's of course is arches and domes for East Texas. This combination in here for the Golden Lane. We have all this extensional faulting with the carbonates above it. And then you get around to the corner. And of course, Yucatan has come down here in the late Jurassic, early Cretaceous. And we don't really know what basement looks like, but it sure did trap a lot of hydrocarbons. So in summary, the SAG and these transgressions are really significant. I think that as an event, they generally are not described very much or recognized what goes on during that period of SAG, and we don't really prospect for them that well. Mesozoic, with the rise in sea level on there, certainly contributed a lot to sealing a lot of these SAGs, as well as deposition of sources and reservoirs. The basement involved habitats dominate numbers and sizes, and it's the trap size, it's not the source rock that limit the field size. So that's the end of the story time. So thank you for your attention.
Well, Richard, thank you very much. It's great to have that world tour of supergiants here. It's definitely a lot to consider in terms of what are the controls. So I'll open it up for any questions first in the room, and then we can go online. Any questions, comments?
No balonies.
How about, I got a question around big stratigraphic traps. You know, you're talking about North Slope, you mentioned East Texas. As a composite, would Guyana qualify as a supergiant?
You know, I think what this shows on there is that our definitions of field, you know, has limits. And when you start mixing lots of styles and depositional events in there and lots of different reservoirs, it's really not the same as the single guy sitting over there. And I don't know really what to do about that. It's just our words sort of fail us on that, because these, you know, you need this block 15 tells you a lot about where it is and what it is and all that. But the fact is, these things can be very, very complicated, and you know, it's a functional thing. For, you know, you've got a big structure and you've got a pinch out on one side, and it's a reservoir, and you got a pinch out on the other side, and it's a reservoir. You might call that one field if one company owns the whole operation. But if you've got Mr. X over there and Madam Z over here, they're going to be called different. And so I don't know how to get around that. I really don't. But basins are the same way. It's just limits. Yes, ma'am.
Yeah. Thanks very much for that world tour. It was fun. I wonder, so you're talking about supergiants, and I wondered what if it's defined on volume, but I wondered if you could break it down into area versus thickness versus porosity. You know, I mean, there's like three things adding up to that volume. Are supergiants thicker, or are they just wider? And how do they rank in terms of pore volume, you know, pore volume multipliers?
The thing that's so different about them is that they are aerially much bigger. Yeah, and that's what's overwhelms it. That's these, for example, these reef plays that are underlain by these basement blocks. They're aerially very, very large, and the limit, the range that you can get for commercial porosity is going to be, you know, from say 10 to 30 whatever percent on there. So you don't have that much of a factor of, well, Yeah, yeah, you got exponents working in the favor of area. They are, some of these things, you know, particularly in the classics, you can get, you know, 1,000 feet of pay sometimes, but that's somewhat unusual. You know, that's like the world's largest oil field. I don't think it's more than a couple of 100 feet, 250, something like that. It's not a, you just don't see huge range. On the other hand, the database behind that is, it's what I'm remembering. What did I see? You know, I didn't notice anything unusual about it. But in terms of consistently seeing a very thick reservoir for these things, you don't. That's not to say it doesn't happen, but as a consistent characteristic on all these things, you could probably put them all together. And you know, if you took all 250 of them, put them together for thickness and just ran a statistics on it, I don't think you'd see that a lot of them were any bit different than smaller fields, you know, 100 feet, 200 feet, stuff like that.
So thank you. That wonderful tour of supergiants. And this is less question than comment, but you've highlighted the role of SAG, which is actually really interesting. And as you pointed out, there are three types. So the thermal SAG, the post-extensional thermal SAG, absolutely. What you've called tectonic SAG, I am that structural geologist who will step up and tell you what it is. It's flexural loading. So as you build topography with the thrust belt, you substitute the weight of the rock for what was formerly air, and it loads the crust, it flexes it down. So as you create a thrust belt, you create that flexural basin in front of it. And you're right, there are some amazing fields in it. But the other thing, the thing that I really wanted to highlight here is that what you're showing is the role of dynamic topography. So, you know, 40 years ago, the advent of plate tectonics focused us on horizontal motions and, you know, lateral movement as a key control. And it put a lot of attention on plate boundaries, absolutely appropriately. But what we forgot about was the role of vertical motions, of pyrogenic uplift. And over the last 10, 20 years, people have realized that mantle convection drives an awful lot of vertical motion. It's a pyrogenic uplift that may have timescales of 1 million to 10 million, even 100 million years, and wavelengths of thousands of kilometers up to half the globe. So Arabian plate, as you pointed out, is a really, really fascinating example of very long-lived, probably dynamic subsidence. And I can put you on to papers about this and about what we see present day with dynamic topography. But it is, I think, the missing ingredient in a lot of what we focus on with exploration. It is a hugely overlooked thing that also controls heat flow, by the way. We see anomalously high heat flows over present day dynamic highs. Things, you know, 40, 50 degrees C per kilometer geothermal gradients. So, as I said, less question than comment, but really interesting tour. Thank you for that.
Okay. Well, I think this thing probably creates more questions than it really does answers in many ways. In particular, I do think that all the SAG events out there can be put together and explained. Maybe they are all different causes in there. I don't really know. It's they're certainly different in their aerial extent. Some of them, you know, well, like the Permian, it runs from Montana well into Mexico. Just the Permian sediments on there. It's a very wide, long-term sort of thing. And just at the end of the Pennsylvania, that thing just started slowly going down. And you know, that's just what it did. And the tectonics on there, I wondered about flexure on there, but I didn't really, in this paper, I didn't want to try to get into the tectonic explanation. What I was trying to do was really to get to what it looks like. And we could figure out how it got that way in another really long and boring paper.
Okay, I got a question. I think all your examples were conventional reservoirs. Where does unconventional fit into this? And are there giants the supergiants and non-conventional too.
Well, the supergiants, there are supergiants in the unconventionals, and I don't know how they fit. That's a different kind of an accumulation. It's a different kind of trapping mechanism, and it's really an absence of primary migration, and that's really why it's there. And whereas this one is the creation of the porosity, and it's and basically preventing it from rising. I don't know how primary migration works, but it's not finished in all these shale plays. And so there's quite different processes involved, and linking the two, it would make sense to try to link these because they're both big volumes on there, but really I couldn't see an easy way to do that. And I'm not sure that they really are. They're quite different processes. So I just plead ignorant, say I don't know.
Sure.
Dr. Bishop, we have a question from online.
Yeah, I was just gonna say, Tip, if you want to unmute yourself and ask the question.
Yeah, sure. Thanks for the talk. Really interesting. I have a couple of questions actually, but I'll start with this one. I'm just curious if you can describe the rate of discovery of these supergiants in terms of the average number per year or per decade that's discovered, and how many might be left out there to find, and if so, where they might be.
There are, let me put it this way, there are multiple prospects published in the literature of supergiants areas, particularly in remote areas. And I didn't know the answer to this. I did just not done that part, but in looking at the discovery years, in the past 20 years, industry has found almost a fifth of all these supergiants. Just in the past 20 years, we have found over 50 of these supergiants, and since the year 2000. Now you're going to say, well, where is it? Well, they're all over the place. A lot of times it's in the big concentrations where the fields already exist. And in the other places, it's in particularly deeper water and better seismic where we can see we have access and better technology to do that. And so finding almost 2 supergiants per year, that's pretty doggone good. I think that's pretty good at pretty encouraging. So, and the remote ones, like Stockman and Berger, their time will come when they will be developed, because the world's going to need a lot of natural gas, and there's certainly a lot of it in the Russian Arctic. I think we probably have a lot in the US Arctic as well. Berger is over 3 billion equivalent, and it just sits there. Same was true with Point Thompson. So the answer is that to your question, I think is that I don't see any reason that these things should stop other than the political situation. So I'm pretty optimistic that we'll find some more.
And if I could just follow up with a second question, how much of these supergiant occurrences do you think is explained by regional charge focus from depth via like some deep structure?
I didn't understand the last of the question. How much of the supergiants what?
Occurrence can be explained by regional charge focus from depth rather than via the deep structure. You talked about the area and the thickness and the unconformities and the seals, but how much of it is related to just being focused charge from a really vast, deep subsurface?
Well, I don't know what exactly you mean by focused charge. I've had some people tell me that fetch area is the key to all these things, and that can be a focused charge. But the thing is, there are a lot of fetch areas that do not have traps. So what happens to that juice? It gets spilled around and slops around the hydrocarbon system. And so I don't really the first paper we wrote on this was on just on prospects and comparing the prospect to what came out of the fetch area and said, well, and the spills, that goes elsewhere and you don't worry about it. But I think you have to be very careful about what these fetch area, using these fetch areas, because I think we have to think about how much juice has been produced by the charge and where's it going to go? Because normally what we don't have a good handle on is how does it go from one trap to another trap or out of the basin when it spills, because these traps are spilling and you can see seeps and so forth out of these basins. So we know it gets out of the basin as well. So I'm not a real fan of limiting just looking only at fetch area. If I look at a prospect and the fetch area says it's undercharged, it doesn't have much in it, I'm going to go look at the next place over and the next place over after that, because there's a whole lot of juice in there that's not accounted for. And you got to figure out where it is most likely to go. So that's the best I can do.
Okay. Any other questions online, Chuck? No? Any other questions in the room? No? Okay. Well, Richard, thanks again. Appreciate it.